Thank you for showing up for the first activity in the new year. And today I will talk about saddle point approximation in an instructive example. And I hope it will be a little bit easier to understand than many of the recent talks we have had. It should be a little bit less technical, but I think it will be very useful, not just in theoretical high-energy physics, but in whatever whatever discipline you're working in, because it's basically just complex function theory. Okay, so what I would ask of you to know on beforehand, that's how to do Gaussian integrals. So let me write the formula that we're going to use. I hope that everybody has seen this before. So if you take and integrate over Rn e to the minus half x transpose some matrix A x, then it's given by the square root of 2 pi n over the determinant of A. Have everybody seen this formula before? Because we will not have time to. It's easy to prove, but we will not have time. And but that's something we should say about it. First of all, for this integral to be convergent, we need that the real part of A is positive. And here I should say this is kind of grown-up notation. So real part of a matrix is obviously real in all of the entries. But what do I mean by that this should be bigger than 0? Any guesses? So what it doesn't mean, and maybe you would suggest, would be that all the matrix entries should be bigger than 0. That's not what I'm talking about. So when an operator is bigger than 0, that's right. So then we need a Hermitian operator which eigenvalues are bigger than 0. That's basically what we need here. It's in that sense. It's not the matrix elements that have to be positive. Is this clear? And when this is satisfied, then the real part of this expression is exponentially suppressed, and then it's convergent. So that's the first thing. The second thing is over here. So the square root is double valued. So usually in physics, we don't talk. I mean, if we have a square root of positive, everybody knows that it's double valued, but we have square root of 4, then of course we think of it as 2, right? So when you see this formula in physics, there's always an implicit understanding by some convention which of the branches we're going to pick. Usually it's something that in our system we have a way to connect to a certain branch, which is more natural than this is always implicitly understood. Is it here also? And then of course that also brings us to how we take a branch cut. So usually if we have if you look at a complex plane set, and so then I have a number here, I have an angle, and I have a here, and I write this in polar coordinates using I set. Then I hope everybody agrees this is going to be a square root r e to the r theta half here, like this. And then I think most sane people would put the branch cut over here. Of course, this is also a choice, but I hope nobody else will insist on another choice. So we will try to do something like this already. Okay, so that's the first thing. The next thing, are the questions to this? This I hope is crystal clear. Then I will go on to what, where the saddle point is used, usually in high energy physics. So it has many names: saddle point approximation, stationary phase approximation, steepest descent method, WKB. So it's many different names which have some overlap. And the point is typically that we have some action, and then we are talking about that there will be some stationary configuration, which we call S50, and then we will expand phi around a stationary configuration 50 plus, and then we put in some quantum correction. And for some reason, I would like to put a square root of h bar here, and then I put a quantum correction to this. And maybe I put a k here, and I'm going to use some here. Of course, maybe you think of this as a vector, but this is really a condensed notation. So I'm really think of this as a field. So k is really continuous and discrete indices, so space-time and indices and discrete indices and so on. So it's a very condensed notation. You can think of it as a vector, but of course, usually in physics, we think of it as a field. And then we now expand the action.
What did you mean by writing S of phi is equal to?
Oh, yeah,
S?
very good. Very good. So we plus corrections. Yes, yeah, well, yes, very good. I truncated this formula. So here there will be extra corrections. So what do we mean by that? This is going to be a stationary point. So we will assume that ds d phi k at phi equal to phi 0 is 0. And so when we expand this, then the first order correction will be absent, and the next order will be what's usually called the Hessian. So there will be h KL 0 plus eta k eta L, and then maybe a half, and then I have introduced HKL of phi should be equal to d squared S d phi k d phi L, something like this. And then there will be higher order, third order in eta, something like this. Is this better?
Where are all the H bars? No.
And then there should also be some H bars. So maybe you will have H bar here and one bar, and then we will have an H bar to the 3½ here. Like this. Is this better? Yeah.
So also what is eta?
Eta is a quantum correction.
So
Quantum fluctuation. Quantum fluctuation. And so it's just a deviation of phi from the stationary configuration, and then for some strange reason I have scaled it with h bar. Square root of h bar. Okay. And then so where are we going to need this? We're going to need this in the particle. So we're going to say set is particle dv phi, and then here I have exponential of I over h bar is phi there, and then first, I will inside the measure of the path interval, I will put in the square root of h bar here. So, and the point is that we would now like to evaluate this path interval in the limit where h bar becomes very small. So like the classical, semi-classical limit of this path interval. And then the point is that since there's an h bar inside here, so when I put in an I here over h bar, I over h bar, then the h bar goes away here, I get an I here, and here I get something which is order square root of h bar over there. Is it clear? And then the argument is that in the asymptotically in the limit where h bar goes to 0, then we can ignore higher order terms. And so in this case, we get the formula reduces to that we have first of all, there will be, the point, this does not depend on the path interval. We can put this outside the path interval. This is just a constant. And inside the path interval, we get, we have to use some kind of infinite generalization of this formula. So first of all, I will not be very careful what 2 pi to the infinite here is. This we will have to somehow renormalize, regularize, whatever. So we will forget about that. But so it will be something like a determinant will be equal to a determinant of, and then I think I get here. There's gonna be because I have a minus here. Then I have to put in a minus in front of here, so this becomes actually I 1 over I h k l, so the determinant of that here, and then to the minus half, and then we get e to the I over h bar, the classical action, classical value of the action. Does that make sense? And then we can immediately make a generalization, because it could be that there's more than one solution to the classical equation for motion, to the Euler-Lagrange equation. So if that's the case, then we call that instantons. So then we would have a sum over instantons, and then we have this formula here. So this is typically what is presented first. I mean, this is like the WKB approximation, 7-point approximation, stationary action approximation. So yeah, so that's the starting point. Is the questions to this?
So I have a question.
Yeah.
So similar to the previous formula, you said that for the integral to converge, the real part of the matrix is to be, I mean, the eigenvalues have to be positive. Is there some similar restriction here on the Hessian of the?
That's right. That's right. So they, so here, yeah. So here, in fact, the function here is more or less a phase, and often if it doesn't converge, so actually, so that's another nice thing. Yeah, I mean, one thing like I said is that we put in an I epsilon prescription to make sure that this real the phase factor here becomes has a small exponential decaying part, so it becomes convergent. But I should also say there's another very intuitive explanation why this is a good approximation, and that has to do with, so I didn't draw that, maybe we can draw it over here. that so we have some configuration. So this is like say stationary configuration, and then we have another configuration phi, and then we are evaluating phi. The point is basically that when we are close to the on shell, so this is on shell, and this is off shell. So when we're close to the on shell, then the action value will change very slowly because it's only a second order effect. And therefore, we will expect that, this phase factor, when we are close to on shell value here, will change very slowly. And therefore, we get a non-trivial contribution that will sum up. But when we are far away from the on shell, then the phase factor will be all over the place, and we will expect it to cancel out. So this is another way of understanding why we can get away with replacing a complicated path integral with just the sum over some discrete instantaneous. Okay, but that also brings us to so let me maybe say we also have the we have a equalization where we take unique time to be the physical time, which is often called Minkowski time, and then we let the Euclidean action be I times the Minkowski action that we have over there. And in this case, the path integral now becomes the Euclidean one, which of course is related to statistical mechanics, becomes something like h bar, and then e to the minus 1 over h bar s e of phi, something like this. And then now there's a minus over here. And in this case, there's no phase, and now everything is real. And what the formula will give in this case will be something like sum over stationary configurations determinant to say Euclidean Hessian to the minus a half, and then e to the minus h bar s Euclidean action. And in this case, we can sort of understand the argument is a little bit different. So if we have S Euclidean, then we can imagine that if this is like a cartoon of our configuration space, then we can imagine that there is some minima, something like this. So this is another configuration. Another configuration stationary here, and the point is here that that this exponential, if the action is big, becomes subdominant. But the biggest contribution, if you should draw this a little bit further down than this one, so this is like the ground state in this picture. This will have because the action is smallest, so this Boltzmann factor will be the biggest for this case. And in this case, we will the biggest contribution will come from the lowest value of the action. So it's very funny, even though it's only equitation from each other, the argument is completely different over here. And also here we have a little bit of problem with maybe we'll say that we shouldn't take this into account because and so on. So it's a little bit strange here, and that actually brings us to the main part of what I want to talk about today, because this is of course formal, and yeah, that's all fine, and so on. But in practice, it's very interesting which of the branches becomes important, which we should neglect, and so on. And this is also known as Stokes phenomenon and so on. So this is what I actually really want to focus on. And to do that, I want to take an example from Peskin Schroeder in one of the first pages, page 14. And I think there they have a simple example. So let me just send this. And I often I don't see often when I discuss this with students, then I often don't see a what's it called, coherent way that this is done. So this is basically what I think it would be very useful to see how we should argue. So what they're looking at is this is Peskin and Schroeder, page 14. And they're looking at an overlap between a position in quantum mechanics and another position where we have we have a Hamiltonian between, and then another position x0. And this is in a discussion about causality. They're trying to Peskin Schroeder at this point. So the physics behind it, you can read in Peskin Schroeder. I'm not going to spend too much about that. But what they're trying to do is to wonder about causality when you have a space-like separation, and whether the correlation there's some correlation or not. I mean, so maybe you know. So one of the way that we say that causality is implemented in quantum field theory is that the commutator between operators should vanish for space-like separated space-like separation. So now, it's in this context that they start to say, okay, let's just take naive quantum mechanics and make the Hamiltonian they take is the first step away from non-relativistic. They say, okay, let's take p squared plus n squared, and then let's calculate that, and then they get a complex integral that they want to evaluate. So let's do that. So I guess x equal to the divided by t square root p squared plus a squared over x0. And so this, I hope everybody understand what's going on. So first, we let's put in a momentum state. So let's put in here an x e is equal to e to the I x e over 2 pi to the 3 pi, and I have put h bar to 1, which, well, Peskin Schroeder put h bar to 1, which is kind of not a good thing here because we probably want to take a limit like this, h bar equal to 0. But so you have to keep in mind that h bar we put to 1, but we might need it for making the steepest descent argument at some point. Okay, so this is equal to over p here over 2 pi to the 3 e to the minus I t square root of p squared plus n squared, and then e to the I p dot x x0. So questions? Is it clear what's going on? And now we have to evaluate this integral. Then we put x equal to difference between x and x0. So it's given by 1 over 2 integral 0 to p squared p, and then I get a cosine integral here from -1 to 1, and cosine I call chi e to the I p x pi e to the minus e square root of e squared plus n squared. And we can do this integral. So I get 1 over 2 pi squared, 1 over pi x. And one of the p goes away, so I have p dp. And here I get e to the pi px minus e to the minus pi px. E to the minus pi square root. Is it clear what's going on? Speak up if it's not clear. So I hope this part is understandable. We're just doing a three-dimensional integral. And here I get after this, so instead of going from 0 to infinite, because I would like to close contours and so on, then I would like to go from minus infinite to plus infinite. So I'm going to write this as 1 over 2 pi squared 1 over r x minus infinite to infinite of dp, and there's a p power here. And then let's call all this to e to the 5 of p. Yeah, sorry for the name, that was just what stuck. My file is the exponential, the exponent. So I'm going to take it from this one. So it's I px minus t square root of p squared of n squared. Is it clear what's going on? So what we're doing is that this here I'm changing p to minus p, and then that gives me the negative part of the momentum. Philip, is it clear?
Yeah, it is definitely the first problem.
It's two parts.
I need to.
Yeah.
Very complete.
Right. So anyway, the Beat is it's good. So we have this integral that we have to calculate, and so here it's clear that we can get this p power down by differentiating with respect to x here. So let's get rid of this p power, and then instead of that integral, we're gonna look at some simplified integral. So the integral we're going to look at is, where do I have that? I don't have it here. Here, I of x comma t equal to integral from minus infinite to infinite dp e to the phi of p. So again, let's analyze this integral, because then we can get that integral by differentiating under the integral sign with respect to x. So we basically, just for simplicity, so we don't have to worry about that p factor. Another way of saying it, if you have done this in one dimension or 1 plus 1, then you would have gotten this. But since we are in 3 plus 1, you got an extra p factor downstairs there. Okay, so this will be what we want to analyze. So we want to calculate this integral with the steepest descent. And maybe I should start. Yeah, so the first thing we have to do is we have to find the stationary points. Right, so phi is this one. So phi is, if you do this, this would be I x minus t over square root of p squared plus m squared, and then p here, and maybe with a parenthesis here, we want a parenthesis, yeah. something like this. This is okay. And we need later also the Hessian. Let's calculate that. So it's minus IT, and then I guess there will be two contributions. There will be one that will be square root, and then there will be plus minus to the 3/2, and then it will be p squared, and then we can put p squared here plus n squared, and then put this to the 3, and then we can subtract. So it becomes something like minus IT n squared over p squared plus n squared to the 3/2. Does that make sense? People are nodding. Okay, so now we have to find the stationary points. So we say, when is this 0? So apparently this is when, so I guess it becomes that x squared should be equal to t squared, p squared over p squared minus n squared, and then plus, and then it becomes x squared, p squared plus n squared, equal to t squared, p squared, and then I put this on the other side, I get x squared minus t squared, p squared equal to minus n squared x squared. And now we can find p. So long story short is that p, that's two solutions, p plus and minus, is equal to plus minus I m x over square root of x squared minus t squared. Oh, yeah, and then of course I forgot to say one thing, actually two things. So one thing is that Peskin Schroeder in this here is interested in space-like separation. So we will assume that x squared is bigger than t squared. So this way will make sense. That's one thing. And then the other thing we're going to assume, well, here we have this integral here. So if we look at it over here, it's a phase, and we have to do an integral over p. So why don't we include some kind of I epsilon prescription so we are sure that this is convergent? And the way we're going to do that is we're going to say, okay, let t be t minus I epsilon. If we do that, then you can convince yourself that the t over here, if we replace that with I epsilon, then we get a small term that would be exponentially decaying, such that now we don't have to worry. Now the mathematicians don't have to roll their eyes anymore. Now the integral actually makes sense. It's convergent. Okay, so we're going to do that. Or since I'm probably not going to write this t minus I epsilon all the time, then you can think of imaginary t as slightly negative. Same thing. Okay. All right. So we have this. This is the stationary point, and the first surprise. I don't know if it's a surprise, but the first surprise is that this is imaginary. And up to now, I don't know about you, but maybe you were thinking that these stationary here, when we were doing the WKB approximation in the path integral, maybe you were thinking that this was like real configurations and so on. And now, here we see now that actually the stationary point is way out in the complex plane. We will be doing integral along the real axis. And what we have been doing up to now is something called Laplace method. And what we really need is something that instead of Laplace method is in the real axis, that you approximate the real axis with the stationary points around that. Here we are going to a much more powerful generalization, which is called the steepest descent method. So this is lesson number 1. We are going to go from that Laplace method in R, and then we go to steepest descent in complex plane. That will be the first lesson that we draw. And yeah, okay, I should say that Laplace we will have maybe stationary points. Stationary points in real, and here we have stationary points in the complex plane. And this brings us to another thing that we want to deform the integration control. Integration control. Using Cauchy integral theorem. So we will integral theorem. Now we do one shot like that. Okay. Yeah. So now, we can take away this here. Are there questions to this? What about the Zoom audience? Is it clear?
Yeah, it's fine.
Sure.
Okay, so now we really need the value of the function, the classical value at these two stationary points. We need the value of phi, and we need the Hessian. Here, this is trivial manipulation. So I'm just going to write down the answer. The only thing which is non-trivial is that, so you see here I had to square the equation, and therefore I have to worry about that I introduce different, sine and square root. I have to check that. And when you do it, then after the dust is settled, you get the following. So we have the p plus minus here, and then it's also very useful to write down what p plus square things square is. And it will be equal to plus minus I n over square root of p squared minus t squared. So here one could maybe think that there will be uncorrelated signs here, but so what I have checked is that every time I use the plus over here, then the consistent choice of the square root is plus, and so on. It's not so difficult. It of course has to do whether this is 0 or not 0 over there. So you have to take this carefully, and you realize that you don't introduce more than 2, and ambiguity of 2. That's good. And the same goes for phi of p plus minus, which now is minus plus n x squared minus t squared. And then, of course, by prime p plus minus is 0, and by dot prime p plus minus is, and that's plus minus x squared minus t squared over 3 over n t squared. This is trivial calculation. The only non-trivial is to get the sign correct.
Well, maybe you can even see it from your equation that you're solving.
Yeah.
You can just take the square root and expand it like pt over x. So if you use p plus everywhere, you get the plus, and the x is cancelled, and you just get that.
Yeah.
That you have over there, the plus.
Yeah.
And if you take the minus, you get the minus.
So
You don't have to do much.
no, it's straightforward. Okay. The other thing we have to the lesson number 2 is that we should pick a direction of steepest descent. So the idea is basically, yeah. So maybe I should before we get to that, maybe let's just make sure that everybody is on the same page about a quadratic function. So let's look at a function f of z equal to z squared, which is of course x squared minus y squared plus I 2xy. And then for some reason I like to put in a normalization of -2 in front. Yeah, but it's still just a quadratic here. So and now let me plot the real part, or minus the real part, z squared. So here we have y, x. So I'm claiming that if y is 0, then it should be something like this. And if x is 0, then it should be something like this. And so it should be something like so I'm trying to draw a saddle. So it be something like this. Does that make sense? Can you see it? Right. I hope that's going to be the best I can do. And let me draw a plot here. Here we have y up x like this one. And then we will say that the direction of steepest descent is along the x-axis. So this would be a line of steepest descent here. And obviously in the y direction we will get a line of steepest ascent up here. And so let me also draw 2 lines here, which I will call, this is where the real part of the function is 0. And so this is in 45 degrees. And so here they will call them anti-Stokes lines. Here. And there will be another one here. Right. There is also, of course, something called Stokes line. And yeah. I'm not going to use Stokes line at all. But I mean, I assume they will be actively there are two in this case. But we will need the anti-Stokes line. They will be crucial in a moment. So this is, I hope this is clear. So now, of course, we have a little bit more complicated situation in general. So now we will look at the function minus 2 to r e to I theta, where this is constant, say complex constant a, and then z squared. So we're going to rotate that function with a complex number like that, and in this case, the contour plot becomes something like y and then x, and then the point is that here we can take away the phase by writing this as r set e to the minus I yes plus theta half squared. Maybe we will before this go down like this. The point is basically that the lines of if we want this again to be the line of steepest descent, then here we should rotate z minus the angle in the negative direction. So we should introduce here. This, yeah. So we're going to rotate this minus theta half down here, and this will now be the line of steepest descent. Is it clear? And then we have something like here, and I should not really have drawn that as high like this would be probably better. And then we will again have the other one here. And I guess it would be nice to put, there's no red. Oh, that's red. So we have there. So we're going to do the same here. So it will be something like this, maybe. And here. Like that. So we have the steepest ascent here. And then we have anti-slopes here and here. Is it clear? There's a high quarter here, something like that. Is clear? Good. So that's the funny thing is that since I mean in this steepest descent, what we are looking at is we just have to look at the quadratic approximation, and the funny thing is that the lines of ascent and descent are always orthogonal, even in the most complicated situation, and it's just an overall rotation, and of course the integral we are trying to calculate is something like an integral from e set e to the minus half r to the e by theta z squared along the real axis. So here, this is the integral we are trying to do. A toy version of that, and the point is now that we're going to rotate this to so we are integrating along the real axis. So instead of integrating along the real axis, we're going to integrate along e to the minus I theta half times the real axis. So it's now I get e to theta minus I theta half times, and then I want to call the new expression variable for w, right up there, and then it's along the real axis, and then e to the minus half r w squared, and this, of course, we know is equal to e to the minus I theta half times the square root of 2 pi over r. That's of course the formula we started with, the Gaussian integral. Or we can write this as square root of 2 pi r e to the I theta under the square root. And of course, here we get precisely a again, as we should. Does that make sense? And well, you may wonder about can I close the contour when I do this shift? And I guess we probably have to assume that theta is less than pi quarter. Anyway,
Well, I mean, you want there to be a real part of the.
so, right. Maybe we can actually rotate it 90 degrees almost.
You want only to be in the part where the real part is negative.
Right,
Uh,
that's right.
so then. Then
Yeah, then cosine. Yeah, I think it's as long as theta is less than 90 degrees plus minus, then I think it's okay. Okay. Now, yeah. So this, so this was just a reminder of what's going on with a quadratic function, how we integrate that. And now let's get back to our integral that we're trying to integrate. And the point is, of course, that we now want to pick the direction of steepest descent. So the point, why do we need the steepest descent? That's of course because if it goes along the steepest descent, then we can use the Gaussian approximation for the longest. And then when the Gaussian approximation becomes bad, then we are so far away down that we can neglect it. That's basically the philosophy of the steepest descent. Does that make sense? I see someone nodding. Yeah. So now we of course have to find the direction of steepest descent in our case. Now I should probably draw a big drawing of the situation. So maybe, well, we need maybe some of this later. So I guess I can actually erase this already. This you have memorized. So let's draw a picture of our interval that we're trying to solve. So yeah. So we have here we have the px, the real p. I take the p plane, and here I have the imaginary p up here, and then I have two imaginary stationary points. And now let's be specific. So let's let x be bigger than 0 and t be bigger than 0. So you have to repeat this 4 times. for different solutions. You just do the first one. The other one, of course, the same, similar. So the first thing is there will be a branch cut of the square root. So where does the square root have a branch cut? Well, the square root obviously have a branch cut at IM and minus IM. Does that make sense? So if you look at the function, so the function phi is long gone. Maybe we should write it again. So phi p will equal to pi x p minus c square root p squared n squared. That's the function we are analyzing in the exponent. And there is a square root here, and then where does the square root have branch cut? It has beside from p because minus p squared becomes minus m squared, right? So there will be a branch cut here, and we will now put the branch cut here and here. So it makes sense around what we have there. Our integration is along the real axis. So we prefer the branch cuts to be far away from the real axis. We pick this. Does that make sense? So that's the branch cut of our square root. Now, where are the decimal points? So we have this one. So notice here that since we are space-like separated, then this one is positive, but it's definitely smaller than that one. So this the stationary points are going to be sit actually in the branch cut. Make sense? But now remember that I let t be a little bit negative with an I epsilon prescription. So maybe I should write that out in.
Yeah, you did the topmost part.
Yeah, I wrote that, but maybe just to see in what direction it goes. So let me write this as the square root. Okay, I'm just going to write square root. So the square root is x squared minus t minus I epsilon squared, which we're going to write as square root of x squared minus t squared. And then I square this out. I can neglect the epsilon squared. So I get plus I epsilon and then sine of t here. Does that make sense? So depending on the sign of t, I would have to put plus or minus I epsilon here. So you can convince yourself that in this case, the branch cut is going to be here, a little bit in the first quadrant here, and a little bit in the second quadrant here. Make sense? Because because you're dividing by a number which has a little bit of positive imaginary part, so it moves a little bit in that direction.
But in our case, sine of t is like we took t.
Yeah, if t is negative, then you will be away.
But the bottom part should also depend on p minus. It should also have one going slightly to the positive side, right?
Yeah, I mean, first of all, this should be first minus in this. First minus right?
Yeah.
So since so the other one sits over here. By the way, there's a plus minus here, so they are going to be completely opposite. So if I did this right, then this would also be right.
Okay.
Make sense? Okay, so that's the first thing. So now, so the naive first thing to do is to say, okay, what about the line of steepest descent? So now look at our the expression for the Hessian over here. So the Hessian here is plus for the positive sign and minus for the negative sign. And remember that here we would like the Hessian to be, or the same derivative to be negative, because we wanted to be over here. So this one is actually the nice one if we just want to have the usual direction. So the line of steepest descent, around this one is actually the natural one. And the line of steepest descent over there is this one. Because it has opposite sign. Does that make sense? I think. Is it clear? Yeah. So the point is basically that that usually, so here is phi here. So phi is we would like phi to be like a parabola in that in the negative direction, right, over there. So so we would like the second derivative to be negative. If we do that, then everything is normal in the real axis. I mean, here. So and that's in fact precisely what happened in for the minus sign here. So that would be that one down here. But the other one had the opposite sign, and therefore it blows up, and therefore we now have to integrate along the imaginary axis, so it comes down again. Does that make sense? Because it's exactly precisely that's the line, the real axis is the line of steepest ascent. So we want the descent one. So we have to put in we have to integrate this one. So I mean the first reaction would probably be if you have to do this yourself, or if you didn't draw the branch cut, then you say, oh, this has the right, this looks like this is the one which makes the actual minus infinity plus. But that's the wrong one, because this one is guaranteed to go into the other Riemann sheet.
Oh, but you could have chosen the branch cut to be
Sure, but yeah, but then I would get into other kind of problems with our but it should work for any choice. So so it should definitely work for this one. And therefore, this will not be right. So it is actually this one. And even though it's quite strange that it actually goes in that direction. And so let me bring you to what the two gentlemen, Peskin Schroeder, is writing. Say, you can. Yeah. So I also totally forgot to say another thing about the integral that we're trying to do here. So the normal thing that when I give this as an exercise, then the student say, oh, I can do this integral. It's a Peskin function. I use I have my table of integrals. Oh, and here I have another in Steinkopf, and so I can see that is an asymptotic expansion of Peskin function. And why, Klaus, are you laughing around this? I mean, then you can of course solve this correct answer. What I like so much about this steepest descent method is that you just, with the help of pen and paper and just calculation, can actually work out the asymptotic, the leading contributions as asymptotic series system. This is very powerful. So now we have found out. Now we basically have the answer. We have to pick this one and not that one. So this we have to take this contribution into account, but not the other one. But let me. Oh yes. So what do they say in Peskin Schroeder? Using the method of stationary phase, the phase function phi has a stationary point at da. We may freely push the contour upwards so that it goes through this point, and then this one. So so this is what they mean. They agree with that. That is, by the way, a mistake in Peskin Schroeder because they didn't. This is only true when x is positive. You can work out for yourself when x is negative. You have to do it. So then you have to push the contour down. Anyway, now let's go to the last lesson. And lesson number 3. Where do I have that? Yeah. We'll show it here. Maybe a little bit more here. So lesson number 3 is the anti-Stokes curves divide the complex p-plane into sectors. The steepest descent contour should only cross anti-Stokes lines, curves at stationary points. Okay, so now let's draw the. So now I'm going to generalize what I call anti-Stokes line before into anti-Stokes curves. So now instead of we will simply ask when is the real part of phi constant equal to its value at the stationary point. And this is actually a quite complicated question. So here, actually, I'm cheating a little bit because I would have to. I'm going to use Mathematica or something like that to actually plot that. So that's not pen and paper. But the result does not really depend. It depends on that. It's just to confirm that we are in the right set. The answer we already have. The answer is given by the formula. But we just want to make sure that we have picked the right set.
Well, you need to show that you can close the contour like
right. So here I'm going to draw. So it turns out that if you calculate this, so this is like for constant real value of phi. Then of course it's going to be near the stationary point. It's going to be more or less across 45 degrees. That we can agree on here. But away it might deviate a little bit. So I claim that that's going to be there's some that goes into the other sheet here and into the other sheet. And then there will be 2, so you see if we can draw this correctly. There will be 2 lines. There's one which goes like this, and another one which goes like this. And this one is just the mirror. So it's going to be one which goes up here and come down, and then another one which goes down. So the point is now that we come here and we want to integrate the contour along the real axis. And so maybe put it orange. So we're going to take this and deform it over here, and it actually gets close to the real axis over here. And we're going to take this one and deform it, and it actually gets close to the real axis over here. So it is actually the correct choice in this sense. And this one, it is actually prohibited to, well, this gets stuck. We cannot get out of this one. We cannot get that to deform it without crossing Stokes lines to get to the real axis.
Well, there's one funny thing. It looks like if you start on the upper side, you have your contour. That's the nice area. And then on the right of it, you have the non-nice area.
Yeah.
Right, the one you want to avoid.
Yeah, this one.
Now on the right.
This one.
Yeah, right. But that's connected to the nice area of the guy below.
Yeah.
Isn't there a Stokes line in between them that you know you have to cross to get from the nice area?
Yes, there's one which comes over here. This one comes.
Oh, but now it looks like I can go from the not nice area with what positive real part of phi to negative real part of phi without crossing any Stokes lines.
This one?
Yeah.
Yeah, but then you're in another dimension.
No. Just start there.
There?
No. There. Yeah, and then go up. Yeah, and then go to the right.
Yeah, that would be.
To the right.
This one?
Yeah.
Oh,
and
yeah.
then go up.
Right, but you would still, this one would still be in the wrong.
I don't care about that one. I mean, I'm just.
Yeah, you can get one of them you can fit in the right direction.
No, I mean, that's not what I'm asking. I'm asking, it looks like, you know, if you look at the stationary point and the bottom,
Yeah.
looks like the area where phi has what negative real part is to the left.
Yeah.
And you can go without crossing anything to the part where phi has positive real part and the stationary point above. I'm just wondering if that is correct and that there is no problem, or if there are some additional Stokes lines. I mean, it might be the case that you know the faces that are the real part which is constant along the Stokes lines has a different value for the above and the below stationary points, and that means that
Right.
you can actually.
Oh, yeah. I mean, the value of the real part of that, the value of that is different from that. Yeah, that's true. Yes.
So it is correct. It's not that you have to.
Right.
There's no other line which you have to cross.
Right. So let's just for completion write down the answer, which you can check. So I guess we can erase this one. So how am I doing this time? I see. Philip.
I have a little problem with my.
Philip is starting. Right. So the point is now that, but I'm more or less finished with what I wanted to say. So here we get sine. You can work out. I'm gonna also write this is negative. So maybe I should start with that. So let's say this is equal to plus minus. That's of course what this we have to worry about. Then we do plus minus here, and then 2 pi over minus pi double prime p plus e to the pi p plus. And then what we have found out is that I, because the contour goes up, so therefore we integrate up, it is plus I. And then it turns out that we have another sign of t, we will have that, and then we get 2 pi over pi double prime p plus, and then we get e to the pi p plus, and this comes out to t square root of 2m p pi n over x squared minus t squared 3/2 e to the minus n x squared minus t squared 4 x squared minus t squared, maybe divided by 85, going to infinity. That's the list. I mean, of course, that's just one example, but I think it has many of the ingredients that you would encounter in a general situation. So I think this is quite useful. So how am I doing the time? I could stop here unless I have one more point I could make, but what time is it? It's 3:20. Okay, so 80 minutes. 80 minutes. Okay. I just want to make one comment that there's also another way. I mean, clearly, this was the way that Peskin Schroeder intended you to do this. But if you look at it, there's also another way, which where you can actually, instead of doing this into the complete plane, then you can actually just rely on the Laplace method. And let me just say how that goes. Just in principle, I'm not going to write down any formula, not that many at least. So the point is basically that you can, if you look at the phi function here, then if you go ultra relativistic, which is important for the convergence of p, when p is much bigger than n, then we can neglect the n in the function. And since x is bigger than t, it's clear that this will dominate in the convergence. So this term is important for the convergence of the interval. So the point is basically that when we want to, we can, since this dominates, then we see that that when, so how to put this, when the real part, when x is bigger than 0, then we could let p go to the positive imaginary part, because then it will become convergent. So if you let the imaginary part of p become positive, then and x is positive, then this becomes negative. So what we could do is we could deform the contour to plane around the branch curve. And of course, we'll do the same with if x is negative, then we have to plane around the other branch curve. So you could. So the point is basically that we could replace with this idea. We get that this is actually the same as the integral along the imaginary axis. So what I'm doing is I'm changing the contour to plane around the imaginary axis, and then I'm going to change my integration variable p to I py, and then we can do the instrument. There's an I here, and then we just get m from branch cut up to here dp e to the minus py x, and then we get 2 hypothetical sinh t square root of py squared minus m squared. Like that. And then everything is real, and then you can just use the class method, and you're fine. And of course, you will find the same answer. But that was clearly not what Peskin and Schroeder had in mind. They said that we had to deform the contour into the complex plane. So, but this is of course another method.
Yeah, but you're also forming complex space.
Right.
So
Yeah.
in this-
But in this, in some sense, it's maybe a little bit more clear what's going on. But I think the other thing is interesting.
So I have another idea that's connected to my question. So it would make more sense if you put the stationary points on different sheets,
Right.
because then you wouldn't have this region which is the good one when you come close to one point and the bad one when you come close to another.
Right.
You know, if I think of it as saddle points, when I put it in the exponential, it would look like, you know, I have a like one somehow saddle point, which is I come down and then I connect to the other one, but in the wrong way. So I have two saddles. One is like and in between somehow I should get 0.
Right. Yeah, it's
So it's like-
it's
so it
not, yeah.
No, it would make more sense to think of the other stationary point, the lower ones on the being on the other plane, so that you're actually the red lines that you have drawn should be like dotted.
Yeah, you want that to the other one. Yeah, I'm not sure you can. I mean, I guess yes. So Richard is asking, raising an interesting question. What does your result depend on the choice of branch cuts and so on? And that's not at all clear that it doesn't. Obviously, it should not. But yeah, that remains to be seen. Good. Okay. Done.
I think in your case, if you say, if you use, like, to put it on the other, plane.
Yeah.
But then if you take, pill-shaped contour for branch cut, then it would again come back here, but then there would be a huge discrepancy between, like, so when Klaus mentioned that you have to have uniformity between, like, different choices of branch cuts. But if they are in different Riemann sheets, then, like, if you have a pill-shaped one, then there's only one. I mean, rather you have the other, but like, you
Yeah.
can choose one that doesn't go through.
Yeah, so as you can see, Russell used the word pill shape to mean this. So he fixed the branch cut here, and this is his pill. that he-
Yeah, yeah, but they could still be on different sheets, and then you don't really see them.
Yeah, but in that case, both the curves are well defined in their own sheets. Like, this will be fine in this one, and that will be fine in that one.
Of course, you can extend, of course, to the sheet. That's totally not saying that that's not be extensions.
Yeah, certainly. More things to think about. I mean, not everything is clear.
Right.
Yeah.
Which is always the case in physics. You're never done. There's always a lesson more to learn.
Yeah, but I'm sure there's not some nice way of thinking about it where it's more clear. So you plotted it with Mathematica.
Yeah, yeah.
Yeah.
Yeah, and in fact, I think I probably just used the Wolfram, and the Wolfram, which is I guess the same.
Oh, you plotted phi,
Yeah.
or real part of phi?
Real part,
You didn't plot the exponential. Now, I'm trying to figure out how the actual studies would look like.
So this is the real plot of with some values. X is 1,3 and M is 3. So M is 3 here. And so here this dot here is not really a dot because some so here the colors are not really because some of this belong to the other sheet. This one is the other sheet. This is the other sheet.
Yeah. Right, but yeah, that would be, oh, so it goes around like that. Interesting. It goes around like that. Yeah. And what is the real value of phi at each of these of the stationary points? That should be easy to
Yes,
compute. Right?
probably deleted that.
We take phi and we put in p plus minus.
Yeah.
So that's like
So phi. Phi plus minus is minus plus and so
okay. Okay. So it's completely real. And the opposite. I see. So in one case, you get something nice, in the other case, things blow up.
yeah. Yeah, so that's also of course a very important feature that we need the exponential to be decaying.
Yeah.
About the Zoom room, you have questions? Or is it clear?
It's okay. Yeah, it was nice. Thank you.
Good. I guess we can stop the recording or.
Yeah. Yeah.
Giacomo?
Okay. Yeah, I stopped recording.
My big head.
Now you can ask questions.
Yeah, one thing, this is semi-classical, right?